October 15, 1943, 32,000 feet above the English Channel. Major Thomas Hayes fought to keep his P-51 Mustang from falling out of the sky. The Allison V-1710 engine coughed, sputtered, and began losing power at precisely the altitude where American bomber formations needed fighter escort most desperately. Below him, 200 B-17s were being torn apart by German fighters. The Luftwaffe had learned to attack above 30,000 feet, where the Mustang's American-built engine gasped for oxygen like a drowning man. Hayes watched helplessly as Bf-109 fighters slashed through the bomber formation, knowing his fighter could do nothing to stop them. The P-51, designed as the perfect fighter, had become a beautiful failure. Fast at low altitude, maneuverable, long-ranged, but utterly impotent above 25,000 feet, where the air war was being decided. The Allison engine, magnificent at sea level, became a wheezing liability in the thin air where bombers flew. In that moment of frustrated helplessness, Hayes was witnessing the crisis that threatened to lose the air war for America. The 8th Air Force was being slaughtered over Germany. Bomber losses approached unsustainable level. Fighter escorts couldn't reach high enough to protect them. The entire strategic bombing campaign, the cornerstone of American air strategy, teetered on the edge of catastrophic failure. What Hayes didn't know was that the solution to his dying engine sat in a British factory, a seemingly impossible marriage of American airframe and British power plant that would revolutionize aerial warfare. The Rolls-Royce Merlin engine, already legendary in Spitfires and Hurricanes, was about to transform the Mustang from mediocre high-altitude fighter into the most dominant aerial weapon of World War II. This is the story of how one engine swap, accomplished against bureaucratic resistance and technical skepticism, turned the tide of the air war, how British engineering saved American strategy, how the P-51 went from disappointment to legend, and how this secret engine fix won the war in the sky. The crisis began long before Hayes watched those bombers die. It began with the fundamental miscalculation at the heart of American fighter design philosophy. In 1940, when the Army Air Corps issued specifications for a new fighter, they believed the war would be won at medium altitude. They were catastrophically wrong. North American Aviation received the contract to build a fighter for the British Purchasing Commission in April 1940. The British desperately needed aircraft and were willing to fund American production. North American, which had never built a fighter, promised to deliver a prototype in 120 days. Chief designer Edgar Schmood and his team worked with extraordinary speed. They incorporated lessons from captured German and British aircraft. They designed the most aerodynamically clean fighter in existence. They used a laminar flow wing that reduced drag dramatically. They positioned the radiator to create thrust rather than drag. The prototype flew on October 26, 1940, exactly 117 days from contract signing, 3 days ahead of schedule. The NA-73, soon designated P-51 Mustang, was stunning. Sleek, fast, maneuverable. Test pilots raved about its handling characteristics, but it had one critical limitation: the Allison V-1710 engine. The Allison was a magnificent piece of American engineering at low and medium altitude. At sea level, it produced 1,150 horsepower. Below 15,000 feet, the P-51 could outperform almost any fighter in existence. But above 20,000 feet, the single-stage supercharger couldn't compress enough thin air for combustion. Power dropped precipitously. At 30,000 feet, the Allison produced less than 700 horsepower. The Mustang's performance collapsed. Climb rate became anemic. Top speed dropped below German fighter. The beautiful airframe was being strangled by an engine that couldn't breathe at altitude. The British, who received the first production Mustangs in October 1941, recognized this immediately. They used the aircraft for low-altitude tactical reconnaissance and ground attack, roles where the Allison excelled. But they knew the Mustang's true potential was being wasted. The Royal Air Force had the solution sitting in their own factory. The Rolls-Royce Merlin engine, powering Spitfires to victory in the Battle of Britain, featured a two-stage, two-speed supercharger that maintained power to 40,000 feet. At 30,000 feet, The Merlin produced 1,460 horsepower, more than double the Allison's output at that altitude. In April 1942, Ronald Harker, a test pilot for Rolls-Royce, flew a Mustang Mark I at the RAF's Aircraft and Armament Experimental Establishment. The experience was revelatory. Below 15,000 feet, the Mustang was the finest fighter he had ever flown. Above that altitude, it became mediocre. Harker immediately recognized what every pilot who flew the Mustang understood instinctively. This airframe, married to a proper high-altitude engine, would be unstoppable. He wrote a report that would change aviation history. The performance of the Mustang with a Merlin 61 would be outstanding, Harker wrote. It would have superior performance to the Spitfire at all altitudes and would revolutionize high-altitude fighter capability. The recommendation reached Air Vice Marshal Wilfred Freeman, who had championed the Spitfire's development. Freeman understood immediately. He authorized Rolls-Royce to begin engineering studies for fitting the Merlin into the Mustang airframe. The challenges seemed insurmountable. The Merlin was larger and heavier than the Allison. It rotated in the opposite direction, creating different torque characteristics. The cooling requirements were different. The supercharger intake needed complete redesign. The propeller would need to be different, but Rolls-Royce engineers, led by Ray Dorey, were accustomed to impossible challenges. They had kept Britain flying during the Battle of Britain. They had continuously improved the Merlin through dozens of variants. They approached the Mustang conversion with methodical confidence. In June 1942, Rolls-Royce received 5 Mustang airframes. They began the conversion that would create the most lethal fighter of World War II. Simultaneously, an American engineer was reaching the same conclusion through independent analysis. Thomas Hitchcock, a wealthy Wall Street banker who had flown with the Lafayette Escadrille in World War I, was now serving as assistant air attaché in London. His connections gave him access to both British and American aviation programs. Hitchcock flew the Allison-powered Mustang and immediately grasped its limitations. He then flew the Spitfire 9, powered by the Merlin 61, and understood what that engine could do. The logical conclusion was obvious. Mate them. Hitchcock began a lobbying campaign that would test every political connection he possessed. He wrote to General Carl Spaatz, commanding the 8th Air Force. He contacted Henry Arnold, commanding general of the Army Air Forces. He leveraged his Wall Street connections to reach Secretary of War Henry Stimson. His message was consistent and urgent. The Allison-powered Mustang was inadequate for high-altitude escort. American bombers were being slaughtered because fighters couldn't protect them above 25,000 feet. The Merlin engine was the solution. America needed to act immediately. The response from Army Air Forces headquarters was bureaucratic resistance. The Allison V-1710 was American. Switching to a British engine would create supply chain dependencies. Packard was already licensed to build Merlins for British use, but converting P-51 production would delay deliveries. The Army Air Forces wanted the P-47 Thunderbolt as their primary escort fighter. Hitchcock persisted with aristocratic stubbornness. He arranged for American generals to fly the Merlin Spitfire. He provided performance data comparing Allison and Merlin installations. He painted vivid pictures of bomber crews dying because fighters couldn't reach them. By August 1942, he had one convert. General Spaatz became convinced. So did General Ira Eaker, commanding 8th Air Force bomber operation. They began pressuring Arnold to authorize the Merlin Mustang program. Meanwhile, in Britain, Rolls-Royce was making extraordinary progress. The first Merlin-powered Mustang, designated Mustang Mark X, flew on October 13, 1942, exactly 1 year after the first Allison Mustangs reached Britain. Test pilot Ronald Harker took it up for its maiden flight. What he experienced exceeded even his optimistic projection. The aircraft climbed like an express elevator. At 30,000 feet, it accelerated with authority that no Allison Mustang could match. The handling remained superb. The range, thanks to the Merlin's fuel efficiency, actually increased. Harker pushed the aircraft to its limit, 441 miles per hour at 30,000 feet, climbed to 20,000 feet in under 6 minutes, service ceiling above 42,000 feet. These numbers surpassed every operational fighter in existence. The British immediately ordered production. They designated it Mustang Mark III and contracted for 1,000 aircraft from North American's Dallas plant. But British production alone wouldn't be enough. America needed to commit. In September 1942, North American Aviation received authorization to install Packard-built Merlins in two P-51 airframe. The program was experimental, low priority, unfunded except for company resources. But Chief Engineer Edgar Schmued recognized the opportunity. Schmued's team, led by Larry Waite, approached the conversion differently than Rolls-Royce. The British had modified the airframe minimally, accepting some compromises. North American decided to optimize everything. They redesigned the entire cooling system, repositioned the radiator intake, modified the fuselage to reduce drag, and engineered a new propeller installation. The first American Merlin Mustang, designated XP-51B, flew on November 30, 1942. Test pilot Bob Chilton reported performance that matched the British result. This was the fighter America needed. But bureaucracy moved slowly. The Army Air Forces remained committed to the P-47 Thunderbolt for high-altitude escort. The P-38 Lightning was also in production. Adding a third type would complicate logistics, training, maintenance. The comfortable institutional inertia resisted change. What broke the bureaucratic logjam was blood. American bomber losses over Germany in 1943 were catastrophic. The 8th Air Force called it Black Thursday, October 14, 1943. The second raid on Schweinfurt lost 60 B-17s out of 291 dispatched. 600 men killed or captured in a single day. The mathematics were unsustainable. At this loss rate, the 8th Air Force would cease to exist within months. Strategic bombing, the cornerstone of American air strategy, was failing. The reason was simple. German fighters attacked beyond the range of American escort fighters. P-47s could escort to the German border and then had to turn back. P-38s had range but poor high-altitude performance. The bombers flew into Germany alone and died. The Luftwaffe attacked with impunity. General Arnold, watching bomber losses climb, finally acknowledged reality. America needed long-range high-altitude escort immediately. The only aircraft that could provide it was the Merlin-powered Mustang. On December 20, 1943, Arnold authorized full-scale production of the P-51B and the improved P-51D. North American's Inglewood and Dallas plants would convert entirely to Merlin-powered variant. Packard would increase Merlin production to meet demand. The decision came almost too late. The first P-51Bs reached the 8th Air Force in November 1943. Initially, commanders remained skeptical. The P-47 had become their trusted mount. Switching to an unproven aircraft seemed risky. Then the Mustangs flew their first deep penetration escort mission. December 1, 1943. Target: Solingen, Germany. 440 bombers escorted by P-38s and P-47s to the German border. Then P-51Bs all the way to target. The Mustangs maintained escort at 30,000 feet. When German fighters attacked, the Mustangs engaged at altitude where they held every advantage. The results were dramatic. Bomber losses dropped significantly. The Mustangs claimed 5 German fighters destroyed for 1 loss. But more importantly, the Mustangs stayed with the bombers. For the first time, American bomber crews saw friendly fighters over the target. The psychological impact was profound. Bomber crews who had faced Luftwaffe attacks alone suddenly had protection. German fighter pilots who had attacked bombers with impunity now faced deadly opponents at every altitude. But the true revelation of Mustang superiority came in the technical details of what the Merlin engine provided. The Packard 1650, as the American-built Merlin was designated, was a masterpiece of engineering that solved problems the Allison couldn't. The 2-stage 2-speed supercharger was the key. The first stage compressed intake air, feeding it to the second stage, which compressed it further. This allowed the engine to maintain manifold pressure at high altitude. At 30,000 feet, the Merlin breathed as easily as the Allison did at 15,000 feet. The Merlin 69, installed in the P-51D, produced 1,590 horsepower at 25,000 feet. Compare this to the Allison's 700 horsepower at the same altitude. The difference wasn't incremental, it was revolutionary. This power translated to performance that dominated the sky. Maximum speed of 437 miles per hour at 25,000 feet. Rate of climb of 3,500 feet per minute. Service ceiling of 41,900 feet. Range of 1,300 miles with drop tanks extendable to 2,000 miles with additional fuel. These numbers meant the P-51 could escort bombers to any target in Germany, fight German fighters on equal or superior terms at any altitude, and return to England. No other aircraft could match this combination of range, altitude performance, and combat capability. Before you hit that subscribe button, let me tell you, the transformation we're about to discuss changed everything. Make sure you're subscribed because you won't want to miss how this engine swap revolutionized aerial combat tactic. The technical sophistication of the Merlin installation went far beyond simply bolting a different engine to the airframe. North American's engineers had optimized every detail to extract maximum performance. The cooling system was revolutionary. The Meredith effect, named after British engineer Frederick Meredith, used the radiator to create thrust rather than drag. Hot air exiting the radiator expanded and accelerated, producing forward thrust that offset some of the radiator's drag. The P-51's radiator installation achieved this more efficiently than any other aircraft. The propeller installation solved a critical problem. The Merlin rotated opposite to the Allison, creating different torque characteristics. North American designed a new propeller mounting and adjusted trim tabs to compensate. The result was an aircraft that handled as sweetly as the original Allison version, but performed dramatically better at altitude. Fuel capacity increased to 184 gallons internal, with options for 210-gallon drop tank. The Merlin's superior fuel efficiency meant the P-51D could fly for 8 hours, covering distances that previously required multiple relay escort. Armament evolved from 4 50-caliber machine guns in early versions to 6 in the P-51D. These were positioned in the wings with ammunition feeds that prevented jamming. The gun harmonization, where bullet trajectories converged, could be set at various ranges to suit pilot preference. The bubble canopy on the P-51D, introduced in early 1944, provided 360-degree visibility. Pilots could see threats from any direction. This visibility, combined with the aircraft's performance, made the Mustang nearly impossible to surprise. But the secret that truly made the Merlin installation work was the intensive engineering that went into integration. Rolls-Royce and North American engineers collaborated across the Atlantic, sharing data, solving problems jointly, refining detail. Temperature management was critical. The Merlin ran hotter than the Allison. The cooling system needed to dissipate more heat without adding weight or drag. Engineers redesigned the coolant passages, optimized airflow through the radiator, and positioned the oil cooler for maximum efficiency. Vibration damping required careful attention. The Merlin's two-stage supercharger created vibrations at certain RPMs. Engine mounts included rubber isolators tuned to absorb these frequencies. The propeller was dynamically balanced to minimize harmonic vibrations that could cause structural fatigue. Engine controls became more complex. The two-stage supercharger required pilots to manage gear change. The fuel mixture needed adjustment at different altitudes. Throttle response characteristics differed from the Allison. Pilot training programs had to teach new techniques. Some pilots, accustomed to the Allison Mustang or transitioning from P-47's, initially struggled with the Merlin version. The different torque on takeoff caught some by surprise. The supercharger gear changes required new procedures. But those who mastered the aircraft discovered performance that exceeded anything they had flown. By spring 1944, P-51Bs and Ds were arriving in theater by the hundred. The 8th Air Force converted entire fighter groups from P-47's to Mustang. The 9th Air Force, supporting ground operations, received Mustangs for air superiority missions. The 15th Air Force in Italy began replacing P-38's with Mustang. The impact on the air war was immediate and decisive. Bomber losses dropped from unsustainable levels to manageable percentages. More importantly, the Luftwaffe began losing the war of attrition. German fighter pilots, who had dominated bomber interception missions, now faced deadly opponents at every altitude. Bf-109 and FW-190 pilots discovered that the Mustang could outperform them above 20,000 feet. What had been target practice on unescorted bombers became desperate fights for survival. March 6, 1944, marked the beginning of the end for the Luftwaffe. The first American fighter mission over Berlin. 174 P-51 Mustangs escorted heavy bombers to the German capital, engaged Luftwaffe fighters over the city, and returned to England. The psychological impact was devastating. Berlin, the heart of the Reich, was now within American reach. The Luftwaffe, which Göring had promised would never allow enemy bombers over Berlin, was powerless to stop them. German fighter commanders understood immediately what the Merlin Mustang meant. General Adolf Galland, commanding Luftwaffe fighters, wrote in his memoir that the appearance of Mustangs over Germany changed the air war fundamentally. "The day we saw Mustangs over Berlin," Galland wrote, "we knew the war was lost. They had range to escort bombers anywhere. They had performance to defeat our fighters. They were in unlimited numbers. From that moment, we fought only to delay defeat." The numbers support Galland's assessment. In 1944, the Luftwaffe lost more than 1,000 fighter pilots per month killed or captured. Aircraft losses exceeded production. Pilot training time dropped from 250 hours to less than 100 hours as fuel shortages and training aircraft losses mounted. The Mustang's contribution went beyond simple kill ratio. Its presence forced the Luftwaffe to change tactic. German fighters couldn't attack bombers without first defeating escort fighters. This forced engagement meant the Luftwaffe was being destroyed in a war of attrition they couldn't win. American production was overwhelming. In 1944, North American produced 5,500 Mustang. Packard produced 10,000 Merlin engines. The training pipeline delivered 600 new fighter pilots monthly. Losses were replaced immediately. Germany, by contrast, produced fewer than 4,000 fighters total in 1944, using multiple types with incompatible parts. Pilot losses couldn't be replaced with properly trained aviators. Fuel shortages limited training and operation. The mathematics of industrial warfare were inexorable. The Merlin Mustang also revolutionized fighter tactics. Previous doctrine held that fighters should stay close to bombers, immediately engaging any attackers. The Mustang's performance allowed a more aggressive approach. Fighter groups began freelancing ahead of bomber formations, seeking out German fighters before they could attack. This offensive fighter sweep tactic, pioneered by units like the 4th Fighter Group, destroyed German fighters on airfields, during assembly, on approach to bombers. The famous fighter aces of the 8th Air Force, Don Gentile, John Godfrey, George Preddy, achieved their victories in Mustangs using these aggressive tactics. They hunted rather than defended. The psychological advantage this gave American fighter pilots was immense. German fighter pilots, who had operated with confidence in their Bf-109s and FW-190s, now flew defensively. They worried about Mustangs above them, behind them, waiting at their bases. The hunter had become the hunted. The technical evolution of the Mustang continued throughout 1944. The P-51D, introduced in March, featured the bubble canopy that became iconic. This modification alone increased visibility so dramatically that pilots could spot threats 3 to 5 seconds earlier, often the difference between survival and death. Engine improvements continued. The Merlin 100 series, built under license by Packard as the V1657, produced 1,760 horsepower with water methanol injection. This allowed brief bursts of emergency power for combat or escaping dangerous situations. Armament improvements included better gun sight technology. The K-14 gyroscopic gun sight computed lead automatically, accounting for target angle and speed. This made deflection shooting, previously requiring extensive practice and natural talent, achievable by average pilots. Range extensions through additional fuel tanks and improved fuel management meant Mustangs could reach targets across Germany, into Poland, and even escort bombers to targets in Eastern Europe. The 15th Air Force used Mustangs to escort raids from Italy to Ploiești in Romania, Vienna in Austria, and targets throughout the Balkans. The strategic impact of this range cannot be overstated. Before the Merlin Mustang, large portions of German industry operated beyond American reach. The Luftwaffe could concentrate defenses at predictable targets within escort range. After the Mustang deployment, nowhere in German-controlled territory was safe. German industrial planning, which had dispersed production to underground facilities and remote locations, proved insufficient. The Mustangs could reach anything. The systematic destruction of German oil production, aircraft manufacturing, and transportation infrastructure proceeded without the Luftwaffe being able to prevent it. If you're blown away by how one engine change transformed the entire air war, hit that subscribe button now, because there's still more to this story that changed history forever. The human element of the Mustang's success deserves recognition. The pilots who flew these aircraft into combat faced lethal opposition, despite their equipment advantages. German fighter pilots, even in declining numbers and with diminishing training, remained dangerous opponents. The 4th Fighter Group, transitioning from P-47's to P-51's in March 1944, initially suffered losses as pilots learned the new aircraft. The Mustang's lighter wing loading made it more responsive but also more sensitive to pilot input. Pilots accustomed to the heavy, stable P-47 had to develop a lighter touch. Major Don Blakesley, commanding the 4th Fighter Group, pushed his pilots to master the Mustang aggressively. "Learn it fast or die fast," he told them bluntly. The group's performance improved rapidly. By June 1944, the 4th led all 8th Air Force groups in victory. The 357th Fighter Group, commanded by Lieutenant Colonel Don Graham, demonstrated what properly trained pilots could achieve in Mustangs. The group shot down 609 enemy aircraft while losing only 137 Mustangs in combat. The kill ratio of 4.4 to 1 reflected both aircraft capability and pilot skill. Individual aces achieved extraordinary records. Major George Preddy shot down 26.83 German aircraft before his death in December 1944. Captain Don Gentile achieved 21.83 victory. Lieutenant Colonel John Meyer claimed 24 victory, all in Merlin-powered Mustang. But the Mustang's contribution went beyond ace victory. The hundreds of average pilots who flew escort missions, never becoming aces but consistently protecting bombers and engaging German fighters, were the true foundation of American air superiority. These men flew 8-hour missions in cramped cockpits, maintaining formation discipline, scanning endlessly for threats, managing fuel consumption, navigating by dead reckoning across hundreds of miles of enemy territory. The mental and physical demands were exhausting, yet they persisted, mission after mission, watching friends shot down, seeing bombers fall, knowing that German flak or fighters could kill them on any sortie. The courage this required cannot be measured but deserves acknowledgement. The ground crews who maintained the Mustangs also deserve recognition. These mechanics, armorers, and technicians kept hundreds of aircraft flying under difficult conditions. Working outdoors in British winter weather, with limited tools and parts, they achieved readiness rates that exceeded design expectations. The Merlin engine, despite its sophistication, proved remarkably reliable in service. The mean time between overhauls exceeded 300 hours. This reliability meant aircraft stayed mission-ready rather than awaiting maintenance. Ground crews developed efficient procedures for rapid engine changes when necessary. The Packard-built Merlins maintained quality standards despite mass production. Packard's Detroit factory employed 35,000 workers building engines. The company invested in precision tooling and quality control that ensured engines met specifications. Rejection rates remained below 2% throughout production. This manufacturing excellence was as critical as design innovation. Brilliant engineering means nothing if production can't deliver reliable hardware in quantity. Packard proved that American industry could manufacture sophisticated British designs to standards matching or exceeding the originals. The partnership between American Airframe and British Powerplant represented international cooperation at its finest. Rolls-Royce shared proprietary technology with a potential competitor. North American incorporated British design elements into an American aircraft. Packard built British engines under license, improving manufacturing processes. This cooperation created a weapon system superior to anything either nation could have produced independently. The Mustang airframe, optimized by American engineers, combined with the Merlin engine, refined by British engineers, produced synergy that exceeded the sum of parts. The strategic implications extended beyond the immediate tactical successes. The Merlin Mustang allowed daylight precision bombing to succeed. This validated the American strategic bombing doctrine that had been failing in 1943. General Henry Arnold's vision of destroying German war production through precision attacks on specific industries required bombers to reach targets, survive to drop bombs accurately, and return. Without effective escort, this was impossible. The Merlin Mustang made it possible. The systematic destruction of German oil production in summer 1944 crippled the Luftwaffe and Wehrmacht. Synthetic fuel plants at Leuna, Politz, and Brucks came under sustained attack. By September 1944, German aviation fuel production dropped 90%. This fuel shortage grounded the Luftwaffe more effectively than combat losses. Training stopped. Operational sorties decreased. The revolutionary Me-262 jet fighter, potentially capable of challenging Allied air superiority, rarely flew because pilots lacked fuel for training. The transportation system attacks, Operation Clarion in February 1945, destroyed German rail network. Marshalling yards, bridges, and locomotives came under precision attack by bombers escorted by Mustang. German troop movements and supply distribution collapsed. None of this would have been possible without the long-range high-altitude escort capability the Merlin Mustang provided. The engine swap that seemed like a technical detail in 1942 determined strategic outcomes by 1944. The Pacific Theater also benefited from Merlin Mustangs, though later in the war. The P-51D equipped fighter groups in the Marianas beginning in late 1944. These aircraft escorted B-29's on missions to Japan, providing protection against Japanese interceptors. The Mustang's range, over 2,000 miles with drop tanks, made these missions possible. Japanese fighters, optimized for agility at lower altitudes, couldn't match the Mustang's high-altitude performance. The few interceptions attempted by Japanese pilots usually ended badly for them. The first fighter escort mission to Tokyo, April 7, 1945, demonstrated Mustang capabilities in the Pacific. 108 P-51's flew from Iwo Jima to Tokyo, 760 miles each way, engaged Japanese fighters over the target, and returned. This mission would have been impossible with any other fighter in existence. The technical challenges of Pacific operations differed from Europe. Longer overwater flights required precise navigation. Engine reliability became even more critical, as ditching in the Pacific offered poor survival odds. The Merlin's dependability proved as valuable as its performance. Japanese pilots' accounts of fighting Mustangs reveal grudging respect. Saburo Sakai, Japan's fourth-highest-scoring ace, described the Mustang as the finest fighter he encountered. "Superior in every way to our aircraft," he wrote. "Fast, well-armed, with endurance we could not match." The contrast between the Merlin Mustang's success and the Allison Mustang's mediocrity illuminates how critical the engine decision was. The airframe remained essentially unchanged. The difference in combat effectiveness came entirely from powerplant performance. This proves a fundamental principle of weapons development. The optimal solution combines the best available technologies from any source. National pride, bureaucratic preferences, and industrial politics must yield to technical merit. The Army Air Forces initially resisted British engines from misplaced nationalism. American engines for American aircraft seemed logical, but the Allison couldn't deliver high-altitude performance. Refusing to adopt the Merlin would have meant accepting inferior capability for political reasons. Fortunately, leaders like General Arnold, Lieutenant Colonel Thomas Hitchcock, and Edgar Schmood recognized that winning the war mattered more than pride. Their willingness to adopt British technology, adapt it to American production, and deploy it aggressively saved the strategic bombing campaign. The industrial cooperation required was unprecedented. Rolls-Royce provided complete technical specifications to Packard. British engineers worked at Packard facilities teaching manufacturing techniques. American engineers visited Rolls-Royce plants learning quality control procedures. This technology transfer built capabilities that extended beyond the war. Packard's experience building Merlins improved their engineering and manufacturing expertise. North Americans' integration work developed capabilities used in subsequent aircraft designs. The P-52 twin Mustang and F-86 Sabre benefited directly from lessons learned. The long-term impact on American aviation cannot be overstated. The Mustang program taught American designers that aerodynamic optimization, systems integration, and power plant selection were equally important. Post-war American fighters incorporated these lessons. The Merlin Mustang's dominance also influenced Soviet, British, and French post-war fighter development. The emphasis on range, high-altitude performance, and multi-role capability became standard. The Mustangs set benchmarks that other designs aimed to match or exceed. Korean War combat proved the Mustang's enduring value. F-82, Twin Mustangs and F-51 Mustangs flew ground attack and escort missions early in the conflict. While jets eventually dominated air superiority roles, Mustangs remained effective in close air support throughout the war. The technical factors that made the Merlin installation successful warrant detailed examination. The supercharger system's complexity required sophisticated engineering to integrate reliably. The first-stage supercharger, driven directly by the engine, compressed intake air. This compressed air then fed the second-stage supercharger, driven through a hydraulic coupling that allowed two-speed operation. Low gear for efficiency below 20,000 feet. High gear for maximum boost above that altitude. The pilot controlled supercharger gear changes manually or relied on automatic systems in later variants. Timing the gear change correctly required attention to manifold pressure and altitude. Poor technique could cause engine damage or temporary power loss at critical moments. The intercooler, positioned between supercharger stages, cooled compressed air before it entered the engine. Cooler air is denser, allowing more fuel burn and more power. The intercooler's design and positioning required careful engineering to maximize cooling while minimizing pressure loss and weight. Fuel octane requirements increased with the Merlin. The high compression ratios and supercharger boost required 150 octane fuel to prevent detonation. Allied access to high-octane fuel, while Germany struggled with lower grades, provided consistent performance advantages. The carburetor design prevented fuel starvation during negative G maneuvers, a problem that plagued early Spitfires and Hurricanes. The Bendix-Stromberg injection carburetor maintained fuel flow during inverted flight or negative G maneuvers, giving Mustang pilots tactical advantages in certain situations. Propeller design complemented engine performance. The Hamilton standard four-blade constant-speed propeller converted the Merlin's power into thrust efficiently across the speed range. The propeller governor automatically adjusted blade pitch to maintain optimal RPM. These technical details, invisible to casual observers, determined whether the Merlin installation succeeded or failed. The engineering excellence that made every component work together seamlessly was the true secret of the Mustang's success. The human cost of developing this capability deserves acknowledgement. Test pilots died proving systems work. Production workers were injured in industrial accidents. Pilots were killed learning to fly the aircraft operationally. Ground crews died in aircraft accidents during maintenance. Captain Glenn Edwards, for whom Edwards Air Force Base is named, died testing a Northrop flying wing in 1948. But dozens of other test pilots died in less famous circumstances, pushing aircraft to their limits to identify problems before operational pilots encountered them. The P-51 program itself was relatively safe by wartime standards. The aircraft's inherent stability and forgiving handling characteristics meant training accidents remained lower than more difficult aircraft like the P-38, but accidents still occurred. Combat losses, while proportionally lower than other fighters due to the Mustang's performance advantages, still totaled thousands of aircraft. Each lost aircraft potentially meant a dead or captured pilot. The improved survival statistics compared to other fighters provided cold comfort to pilots who didn't return. The Mustang's success story often overshadows the human cost of creating and deploying. Thousands of people, from designers to factory workers to pilots to ground crews, contributed to the aircraft's effectiveness. Many paid with their lives. The strategic assessment of the Merlin Mustang's impact on World War II must acknowledge both military and industrial dimensions. Militarily, the aircraft enabled strategic bombing to succeed. This destroyed German industrial capacity, crippled transportation, and eliminated fuel production. Industrially, the program demonstrated American manufacturing superiority. The ability to produce 15,000 Mustangs in 2 years, while simultaneously building tens of thousands of other aircraft, proved American industrial capacity exceeded Axis capabilities by orders of magnitude. The international cooperation aspect, American airframe with British engine, foreshadowed post-war NATO alliances. The lesson that allies combining their strengths could overcome any opponent remained valid through the Cold War and beyond. The Mustang's post-war service life extended decades beyond World War II. Air forces worldwide operated Mustangs into the 1980s. The aircraft's sound design and robust construction allowed upgrades and modifications that kept it relevant long after contemporary designs became obsolete. Racing Mustangs still compete at Reno air races, achieving speeds exceeding 500 miles per hour. These modified aircraft prove the basic design's excellence. 70 years after initial deployment, Mustangs still fly regularly and reliably. The lesson from the P-51's secret engine fix extends beyond aviation. Complex problems often require combining the best available solutions from any source. Pride, politics, and tradition must yield to effective. International cooperation, while bureaucratically difficult, produces results superior to isolated national effort. The engineers, pilots, mechanics, factory workers, and commanders who created, built, flew, and maintained the Merlin Mustang changed history. Their collective effort, coordinated across 2 nations and thousands of individuals, produced the weapon that won the war in the sky. Franz Stigler, the German fighter pilot who escorted Charlie Brown's damaged B-17 to safety, later reflected on what the Mustang meant to Luftwaffe pilots. "When we saw them over Berlin, we knew the end had come, not because they were superior aircraft, though they were, but because they represented American industrial power we could never match." The Merlin engine, designed by British engineers, manufactured by American workers, installed in an American airframe, and flown by American pilots, symbolized the Allied coalition that defeated fascism. The technical achievement was remarkable. The cooperation required was unprecedented. The strategic impact was decisive. The P-51 Mustang's transformation from mediocre high-altitude fighter to dominant weapon system resulted from one critical decision: install the Merlin engine. That decision, made in 1942 against bureaucratic resistance, changed the course of the war. The secret wasn't really secret. It was hiding in plain sight. The best available engine married to the best available airframe. Simple in concept, extraordinarily difficult in execution, ultimately decisive in outcome. The Merlin Mustang won the war in the skies by making strategic bombing viable, destroying the Luftwaffe in a war of attrition, and providing range that put all German territory at risk. None of this would have been possible with the Allison engine. One engine swap, one bureaucratic decision, one technical solution. These changed history. The pilots who flew these aircraft, the engineers who designed them, the workers who built them, the mechanics who maintained them, all contributed to the victory. The P-51 Mustang with its Merlin engine stands as proof that optimal solutions require combining the best available technologies regardless of source. That international cooperation produces superior results to isolated national effort. That technical excellence properly applied determines strategic outcomes. The beautiful fighter that couldn't breathe at high altitude became the weapon that dominated the sky. The secret engine fix that seemed like a technical detail became the solution that won the war. And the Mustang, powered by British genius and American determination, earned its place as the finest fighter of World War II. From October 1943, when Major Thomas Hayes watched helplessly as his Allison Mustang couldn't reach bombers being slaughtered, to May 1945, when Mustangs escorted the final missions over Germany, the transformation was complete. The engine swap that bureaucrats resisted, that seemed logistically impossible, that combined British and American technology, had decided the air war's outcome. The secret was simple. The execution was brilliant. The result was victory. The P-51 Mustang, powered by the Rolls-Royce Merlin, won the war in the skies.